Okay, let's see now. Okay, this is driving force is equals to longitudinal direction of Fg. Okay, so because it moves, the water moves to this direction, right? And once you have this, this is the slope of the channel, which is theta, and then the theta is also can be observed here. Okay, so you want to find this. Okay, this is Fg. Okay, so you know that Fg, this one, is equals to, when you divide by weight of water, you will get sin theta. Okay, because this is actually from this diagram, right? This is theta. You want to know the Fg, right? And then you already know the weight. This is the weight of water, right? Okay, like in the previous, oh my god, no, this is not good. Okay, like in the previous video slide where you have this object falling down, then this is the weight. This is the weight equals to mg, right? And the upper force, the force going to the opposite direction is the drag force, right? So this is F equal to mg. Okay, so mg in this case is weight of water. Okay, but you want to know this longitudinal force, right? So sine theta is equals to Fg divided by weight of water. Okay, this is how you derive this Fg. Okay, so it's like this equation. Alright, so Fg is equals to then weight of water multiplied by sin theta. Okay, weight of water is equals to this equation. Density times G times volume of water. So density times G is equals to unit weight, like you see here. And then volume of water is A multiplied by distance. So how do you know A? So imagine if you have, okay, like this one, this is cross-section view of A. Okay. And then you multiply by the distance here. And then you can get the volume. Okay. And then, okay, since this is weight of water, so you can plug in this equation into the equation of gravity force. So gravity force at this direction, longitudinal direction, like this, is equals to unit weight times A times distance of x times sin theta. Okay? But remember, you also have resisting force. So resisting force is simply this equation. Okay, this is tau, tau 0. Tau 0 is shear stress between the flowing water and the wetted surface of the channel. Okay, so if this is the cross section, so this is what it is about. The shear stress occur here. Okay, and then you have P. P is wetted parameter. So wetted parameter is also measured at this surface. Okay, wetted parameter. So so for example, if you have this kind of channel, open channel, so this is the wetted parameter, the perimeter yang basah, wetted parameter. Okay, and then you multiply by distance of the water move. Okay, so when you have this condition, driving force is equals to resisting force, then you have uniform flow. Alright, so you combine these two equations. Let's see, this equation and this equation is combined, so you can have this. Alright, equation 4.6 as in your textbook. Okay, okay, now since we know this equation 4.6, okay, so you divide both sides by the wetted surface area of the channel. So you divide both sides with this, and then you can get this equation. So this is equation is from equation 4.7. and A over P is hydraulic radius. So this one, yeah, from this equation it becomes this equation, and this is called hydraulic radius. Okay, you can read the explanation here. This is from textbook. This is how from this equation we get to this equation, explanation about sine theta and also about tan theta. Okay, so now since we have this equation, and tan theta is actually equals to S slope. The slope is equals to rise over run. Rise over run means rise over run. Okay. Okay, so this is very helpful. Later, if you want to solve the problem, you can see how can we use this equation. Okay, so finally we have this equation 4.9, unit weight time hydraulic radius times slope is equals to tau 0. Okay, so which S to use? Because in the case of in the case of open channel flow, we can have two types of S. Okay, S is slope. Yeah, okay, if you look at this example, this figure, this is figure 4.4 in textbook. Okay, so this is figure 4.4. Okay, first there is this total energy line, and you also know this is hydraulic energy line. I guess this is explained already in the first lecture of open channel flow. Okay. Okay, so in this total energy line, there is a slope. So this slope is called friction slope. Okay, and there is another slope. This is the slope from the channel bottom. Okay, so this is slope. We call this slope SO, channel bottom slope. Yeah, this is channel slope. Okay. So in uniform flow, SF is equals to SO. Okay, so in this equation, you are actually using, okay, in this equation, you are using friction slope. Okay, because now you are dealing with friction. But bear in mind that actually SF is equals to SO in uniform flow. You have to know this. Okay? Okay, let's see now how all this can be used to derive cheesy equation. Okay, we already have equation 4.9 here. Okay, and this is equation 4.9 as we derive here. Okay, and then you also know that this friction, this shear stress, this shear stress is proportional to velocity. Proportional to velocity. Okay, so by combining these two equations, we get V to the power of 2 is equals to C times 2G times unit weight times hydraulic radius and times slope, friction slope. Okay, so this part of this equation is considered as C, constant. Okay, and from here you multiply by R and F, and then if you square root this V, finally you can get this equation, and this equation is Chezy's equation. Okay. Okay, so this is you can find this equation in equation 4.13, and here C is equals to this equation, and this is actually derived from Darcy-Weisbach. It's in the textbook, but I don't think I need to tell you for this syllabus. You can just use it. Okay, but we know that this is derived from Darcy-Weisbach. Okay, so this is finally Chezy's how Chezy's equation is derived. Yeah. Okay. After knowing about Chezy's equation, now we are going to look at Manning's equation. So if you still remember, this Manning equation and Chiz's equation is to explain about the friction that occurs in uniform flow of open channel. Okay? So Manning equation is similar to Chiz's equation with a slight additional dependency on the hydraulic radius and a different presentation of the roughness coefficient. So this is from Professor Moglen from the textbook. So he explained it like this. Okay. So this is the equation for C. Okay. Roughness coefficient. This is so C is Chiz's roughness coefficient. N is Manning roughness coefficient. So this is how Manning is included in the Chiz's roughness coefficient. Okay. And K is either 1 if the velocity is reported in m meter square. But if K is reported in English unit, so there will be a different value for K, which is something like 1.4. It is in the textbook. Okay. So from here, we can get Manning equation. So this is Manning equation. Okay. So in the author's experience, Manning's equation is more widely used than Chiz's equation, perhaps for the simple reason that Manning's n is apparently independent of unit. So dia tak bergantung kepada unit. So that's why Manning equation is more widely used. Okay, so this is according to the Professor Moglen, the professor who wrote the textbook. Okay. Okay, so these are the values of n. So we don't have to identify n. We can just use from the table. Okay, for example, if you have pipe with different surface material like neat cement, concrete, or sewer pipe, so all these are the value of n. If you have line channels, these are the values. And if you have unlined channels, if you have something like vegetated, something like this, Bermuda grass, or if you are using other types of grass, then you can have different n, different coefficient of Manning. Okay, so you are going to use this value when you want to solve the problem later. Okay, so in conclusion for today's lecture, we have two equations to describe resistance in open channel. Okay, so resistance, or we can also call it friction. So friction in open channel can be described by Chiz's and Manning's equation. So these are the equation, and this equation is from the terms of velocity, right? So V is equals to C squared R times S. This is also V is equals to K over N, R2 to the power R to the power of 2 over 3, S to the power of half. Okay, and then you use this V in the equation of continuity, which is Q is equals to AV. Okay, so now you can use this equation. Okay, so this is taken from Manning. Okay, if you have any open channel with friction and you want to know the Q, so you can use this equation. So we will do this exercise later in my video. I will share with you. And if you want to also try by yourself, you can always do that from the textbook. Example 4.1. So I'll see you in the next video. Thank you.